I'm Jonathan Morefield of Handel Architects. I'm joined here by teammates Paul Lenke and Stefan Di Leo. And we'd like to start with a big thank you to John Kraus and Peter Schmidt and Mitchell Bring of Boston Valley Terracotta, Omar Khan and the University of Buffalo Architecture and Planning students that we collaborated with, Andy Brayman of Matter Factory, our collaborators, D. Simone Consulting Engineers for their facade engineering help, as well as like a big thank you to all the collaborators we had in our office, led by partner Gary Handel. It was quite a big team. It was a big collaborative effort. So we initially kind of approached Boston Valley Terracotta to get involved in this program after following for many years and being really excited about all the different uses of terracotta. And we've often looked at it in our own office, but we're kind of hoping to use this as an opportunity to advance kind of the sustainability aspects of it. So our initial foray into it was looking at this kind of tensile structure as a way to maybe make a facade system that would reduce the connections to the building. We looked at like a one-way, a two-way, and a three-way system, but initially kind of pursued the one-way system at the beginning. And so we made a mock-up of this and just to see if it worked, and it did. And then we started to kind of flex it and realized that we had this great potential for this kind of malleable form, really sinuous sculptural thing that could be tweaked. And then as we looked at it, we thought like, you know, this can also just not just be the disc, but we can also start to put panels on top of this that could be almost any kind of shape and start to look at performative aspects of those panels. Along the way in our research, we were looking at kind of both systems in nature and in architecture of shingling as a way to get some sort of performative system of a brise-soleil or a cladding system. And as we started to kind of explore the geometry and like looking at this kind of scaling aspects and look at how the heat dissipation might work with the different shapes. And then we also started really getting into the performative aspects of could we coat this in a PV panel as a way to kind of further the sustainable agenda. Ultimately, you know, in our research, looking at like ways of carbon capture or capture solar capabilities. In a lot of our research, we just found like it wasn't quite there, and then in the firing process that the solar panels may not hold up. So we kind of hit a dead end in looking at ways to really do much with the coatings on the panels.
Yeah, hi, this is Paul Lenke from Handel Architects. I'd like to kind of add to this a little bit as we kind of talk about the kind of performative research that we did. You know, we looked a lot at titanium dioxide coatings and as well as kind of natural solar PV coatings. And we reached out to a lot of scientists and kind of industry experts. And ultimately it wasn't, you know, the conclusion isn't that this stuff is impossible, but that the technology as currently developed doesn't allow these kind of natural I guess, molecular compounds to survive that firing process. And so, you know, in the spirit of it being a ceramic exercise, we didn't just want to like laminate solar PV into a piece or, you know, spray on a titanium dioxide coating that would need to be reapplied over and over again. So at this point, we kind of decided, let's go with the system that we've developed and try and figure out how far we can push that in terms of executing a kind of exterior cladding system that's really dynamic.
So kind of our initial look was this tiling method of trying to get some apertures that would allow light into the system in this one-way kind of system with these shingling, but.
Yeah, so I guess from here, I'll kind of take over the conversation. And, you know, we had initially, you know, we've been working very closely with D. Simone Consulting Engineers in their facade consulting department. And we initially had kind of engaged them about this one-way system. And there was a bit of back and forth, and at first we thought we could make it work. And then as we got into the detailing of the connections between these terracotta pieces, you know, the way that this one-way system works is that basically it's gravity loaded, and then you are putting these kind of terracotta units in compression against each other. And we really loved that clarity of the diagram and using the compressive quality of the material to you make the system work. But the reality of that diagram is it also was kind of the failure of the diagram, in that if one piece breaks on an exterior facade system, you have a problem of progressive failure. So, you know, we really were heartbroken that we couldn't figure out a way to make that structural diagram work, because to us it was so pure and compelling. But ultimately we had kind of looked at multiple structural systems, you know, with these tensile cables, and immediately kind of pivoted to a two-way pre-tension system that kind of manifests itself in more of this diagrid pattern. And I think that that was a testament to our team's creativity and our ability to kind of adjust on the fly as we were kind of going through this science project like research process. And so from there, we basically said, you know, how can we make this system as interesting and flexible and pliable as what we were, we had previously. And, you know, we came up with, since the cable system was pre-tensioned, we came up with this idea that, like, what if the pieces could actually pivot within that system, not just kind of have the system mapped to a ruled surface or kind of complex geometry. So, you know, you can see some of these early diagrams of us, you know, thinking through this kind of 10-degree rotation as this gradient that kind of goes from 90 to 0, you know, where this is this shingled system that is more of a closed rain screen, and then this becomes like an open brissolade. So, with some imagery here. And, you know, this was our kind of initial concept for this, you know, part 2 of our research and design project. And, you know, so basically, you know, then looking at the actual module and like how we would need to kind of shape that piece in order to allow that pivot to happen, you know, clearing hardware that would need to be pivoted past, you know, making sure that we had sloped surfaces so that we could get the kind of rotation past the cables without any interference and within a certain amount of tolerance, but still maintain this kind of like scale like aesthetic that we really liked in terms of the kind of analogy to the exterior system development. And then, you know, next step was really like starting to kind of project like how this could aggregate on a facade. You know, would it be unitized with pre-tension cable systems? And then, you know, would these pieces be installed in the field or like on the deck, you know, in the construction site? You know, trying to think through all of these kind of fabrication and also installation problems, you know, even though as architects, a lot of times it's not our job to think about these things. I think in this process where we're collaborating with fabricators, it really became part of our interest and things that we wanted to make sure we thought through, particularly when this was going to be an in-person VMU where we would be assembling it ourselves in Buffalo, which unfortunately is not the case, but, you know, at the time we were hopeful that it would be. So, and then we really got into, you know, what does this piece shape like? And, you know, how does that shape start to kind of inform some of the precedent imagery and like kind of inspirational kind of content that we had, you know, had previously. And this is kind of a progression of like, you know, a single image that kind of shows a couple different studies. And we ended up kind of settling on something relatively similar to what's on the right. And, you know, this is kind of the manifestation of that geometry. You know, we created this kind of ripple brow line, you know, along the bottom to really kind of catch the light and, you know, give us some interest when we get into the glazing process. And then the rest of the shape was really kind of driven by function of needing to kind of rotate through the cable system and be anchored to the nodes. So, you know, other thing that we kind of got into on this, which I think was kind of interesting and part of the kind of discovery process, was that, you know, by using you know, playing with the material of the base clay, you know, and the requirement that a certain side of this would need to be unglazed in order to sit on a kiln shelf and be fired, you know, we really started to say, well, we can have like two colors, right? You know, when you have an exterior glazed face that is then, when the system is closed, one color, and then when it kind of dilates and opens and becomes this brisole, that from below, from the kind of perspective of the pedestrian, exposed a natural terracotta behind. We were really fascinated by that, and we thought the lighting effect at night and how this kind of system changed its character from daytime to nighttime became super fascinating. And you can kind of see here the scallop that is generated from that required clearance for that that connection node, and that became like, you know, these little details and performative aspects of the piece became really fascinating to us. You know, so I'm going to speed up a little bit here, but we you know, this is an exploded diagram of kind of all of the different parts and pieces. You know, because we were building this ourselves, we tried to really limit ourselves to off-the-shelf hardware. I think, you know, if this was to be a real facade on a project moving forward, that we would probably take a much more custom approach. But, you know, this really was us trying to limit the amount of custom components so that we could have this fabricated and actually built at University of Buffalo's facility now. But, you know, instead we're, you know, trying to at least document and show you guys this virtually. So yeah, and then this is kind of an image from the exterior side of our virtual exhibition space, and kind of to show you the kind of final manifestation of like what our vision for what this could be, you know, from the outside. And you'll see some other images further in the presentation and in the exhibition space of how this can be viewed from interior and also as an interior installation when it's not on a facade. So on that note, I'm going to hand it over to Stefan Di Leo, who's going to talk about the glazing and fabrication that we've been working on with the Matter Factory.
Hello, everyone. So for the physical pieces themselves, next.
Yep.
So this is our actual VMU that we're going to mock up. And you can see that individual pieces here, as they're, one thing that you'll notice is that they're not all rotated in the same angle. Toward the bottom, they're planar to the rig behind them. So we're actually seeing most of the surface. And as you move up, they're kind of rotating out of plane so that we're seeing them foreshortened. And that color change in between the green at the bottom and this kind of silvery, metallic, almost white in appearance that we're seeing towards the top is a result of the glaze. So that's something that we'll look at next. These are some images of the process. We are in the slip cast portion of this presentation, but we also kind of designed this terracotta piece to be ram pressed also, with the idea being that if we are deploying this across an entire facade, it would be fast to kind of ram press it. So in designing it, we kind of tried to make sure we didn't have any undercuts. And you can see that the back here is hollowed out to kind of reduce the weight, since this entire system is suspended by a tensile structure. The goal was to have it be as light as possible, and also to distribute the weight in the module itself to kind of allow it to pivot without putting too much strain on the pins themselves. Next. Here you can see a close-up of the connection, that portion there that's hollowed out. If it was ram pressed, there would be a post-processing. We would tool that out to receive the mechanical connections. And you can see here also the more ribbed geometry on the bottom was actually created to support this, this module as it dries and as it goes through the kiln, to make sure that it's taking on its true form that we designed through the baking process, the firing process. Next. This image here, you can see them on the shelf before they go in the kiln. And this is good to see the ridges that we tried to design. We designed those to kind of capture the light in a certain way, and also once the glaze is applied, to allow for some differentiation and visual interest in the surface of the pieces themselves through allowing it to pool kind of in the troughs and be a bit thinner on the ridges. You'll see that in the next few images. Next. Here are some inspiration photos. Similar to kind of the form of the module itself, the individual terracotta pieces, and the overall aggregation of them as scales. We were also inspired by nature for the glazing themselves. Iridescence is something that we've all seen before, but kind of has this magical performative aspect to it. And we tried to capture that. So the idea is that we were looking to create a color change that we see in kind of soap bubbles in the exoskeletons of beetles, feathers, butterfly wings. We see it on the interior of some shells. And that's what we worked with Andy Brayman at the Matter Factory to try to reproduce. And next, we went through hundreds of different tests. And next. These ones are showing some of the, more clearly show the iridescent effect that we were going after. And next. And this is one of the two kind of final approaches that we went for. This is showing kind of a deep green color. And then you can see some of the bronze on the edges as the surface changes, or as your angle, your view angle to the piece itself changes. And next. And this was kind of the kind of secondary direction we were also going, which was more of the opalescence, the kind of the milky, the foam, the soap film texture. So at one angle, you can almost see the clay body through it. And you have this kind of light, subtle, beautifully rich texture. And next.
Stefan, we got to pick it up.
Okay. And next. And then as the light kind of changes, you can see the soap film reflection. Yeah, you can see that in this final image. And some of the tests all together.
So to kind of finish up here, we just wanted to kind of show some images of our kind of virtual exhibition space and encourage you as the participants to download the exe file that is accessible on the ACA webpage, where you can kind of see the kind of full extent of our kind of virtual exhibition space, where we've also not only deployed an exterior application, but also a very large scale interior application, which has all of the parts and pieces in it that are integral to our system. So feel free to get up close and check it out up close in person. We have the exploded model in the center space that we showed in one of the slides previous. So you can see all those parts and components individually, and then kind of our full set of imagery that we presented today, in addition to some additional images from the fabrication and design process. And then again, the exterior application, which you can get up close and personal with as well, and also kind of go outside and fly around and look at it from the outside. But on that note, that's it. Thank you very much. Hand it off to the next team, I guess.
Yes.
So I am Mario Romero, a computational designer here at Perkins and Will.
I'm Juliette Zidek, an architect at Perkins and Will.
And Hogan, designer at Perkins Will.
Angelica Paleczny, a designer at Perkins and Will.
Okay, so just to dive right in, I'll be introducing our project and discussing what ideas and goals really drove our design studies for the workshop. Our team is all actually lucky enough to work at the Wrigley Building in Chicago. So for those of you not as familiar with its architectural history, the Wrigley Building is really a landmark high-rise building located just north of the Chicago River and constructed almost exactly 100 years ago. It is clad entirely in terracotta. It has this beautiful gradient of white terracotta tiles that change in brightness over the height of the building. So up until mid-March, we had this as a beautiful daily muse for this workshop, and throughout our design process, we often considered how our fabricated assembly would look juxtaposed with the Wrigley Building as a backdrop, as you can kind of see here. But beyond that, what really first inspired our group's design explorations was learning about the history of terracotta and its use in architectural and infrastructural applications. Through research, we found that in addition to being used in sculptures, bricks, tiles, and ornamental objects, terracotta has been used to transport water for thousands of years. The first terracotta pipes came into use around 4000 BC, and because of terracotta's unique resistance to the corrosiveness of acidic wastewater, some of these ancient plumbing systems actually still exist today. So with that relationship between water, terracotta, and its history in mind, our team framed our design studies around the question, what are the limits to controlling the flow of water across a vertical facade system? We became interested in exploring how a terracotta facade system could be designed to accept, control, ultimately harvest, and recycle rainwater. Through this series of sketches, we started to study, what does controlling the flow of water mean? We first thought about how to slow the water's gravitational flow by directing it horizontally across the face of the facade, and potentially through the facade to an internal collection system. Through this process of intentionally directing and slowing the flow of water, we would be able to leverage the terracotta for evaporative cooling and water filtration processes. The sketches to the left study how the geometry of the module could achieve this end in a dynamic and engaging way.
And so I think one of the first things that we began to experiment with was testing different variations of the grid that the panel system can actually inhabit, and mostly working through a standard square grid and hexagonal grid. Here, I think what you'll see is kind of what we consider three of our most critical experiments in terms of form finding and surface articulation. The first was tiled the catcher. This started the notion of having a central void space and also a potential for a surface expression to try to catch and direct water flow. And so it's sort of this stepped terraced panel piece with the center space removed. Then following that experiment, we created this, what we call the Stretch Hexagon, carrying through this notion of the ridging that we originally had with the previous panel, as well as potentially directing the water flow in a more vertical orientation, so up and down. You can kind of see that the ridgings create a sort of fluted negative space. And then finally, we landed on what we call the finned hexagon, which tested compressing the previous panel into a standard hexagonal grid and seeing sort of what that brought about in terms of like movement and direction. And so through these early prototypes, we realized that the articulation of the surface panel and a void space was something that we were really interested in pursuing. Secondly, we began to appreciate the intersections of the hexagonal grid much more than the hexagon itself as a panel. And so this led to the creation of what we deemed the 3-point module, which you can see here on the right. And then with further experimentation, focusing on ways in which we could control, manipulate, or direct water movement across the face of the panel, which you can see here. We started experimenting with potential ribs, with fins, with what happened if we twisted the face of the 3-point panel. And finally, that led us to the funnel diagram, or the funnel panel here. And you can kind of better see that funnel three-dimensionally here. The funnel was sort of a turning point for us. It was the moment that we began to treat the panel not as just a single kind of face or a single facing panel system, but as a dual panel system with, again, this notion of void space in the center connecting or bridging the two faces. And so once we settled on the panel geometry, we began to further experiment with the ridging that was introduced in the earlier prototypes. And so for this, we decided not to force a sort of set pattern on the panel, but rather use or express the panel's topology and experiment with differing ridge types. And you can kind of see our three primary experimentations with those ridges. So on the right, there was the smooth panel. And what that was just basically both peaks and valleys of the ridging were smooth and rounded. And you can kind of see the cross section here. Then the creased ridging. And so that's where peaks are smooth and rounded, but the valleys of the ridging are kept sharp. And then finally, the sharp ridging, which is both peaks and valleys are sharp. And so through prototyping and 3D printing and prototyping and testing physically, we actually took these small segments, 3D printed them, Andy at the Matter Factory actually ran these tests, glazed them, and fired this out of ceramics, and was able to test water flow on these surfaces. And what we found was actually the sharp ridges carried and flowed more water more effectively than the rest. And so that's sort of what we ultimately went with in terms of the final ridge design or ridge patterning. And Juliette, do you want to talk about the structural portion?
Oh, yeah. Right. So to further the development of the module design, we analyzed the structural performance of the terracotta facade module as an unsculpted mass under self-weight, so that we could look at where there was potential to remove material and enhance its structural performance. So we load it with its self-weight and an applied wind load, and this diagram shows the internal stresses of the module, and the orange zones indicate areas of low stress.
And then kind of going back to that 3-point module, I think we could talk a little bit about what we sort of were experimenting with as well.
Yeah, so Mario started to talk a little bit about how we were studying the ways that these varied ridges and valleys really started to inform the way that the flow was creating across the module. So when we stepped back and really looked at it, not just as a singular kind of cutout of the module itself, but as a full piece, we really started to understand like these secondary dynamic flows that started to inhabit the modules as they were put together. Which we found very interesting, such as, you know, creating the grooves allowed for much more of a quick slide versus the cliffs allowed for a nice slow drip off the modules. And if we go down a little bit, an additional concept we started exploring was the option of maybe can we do something that's a plug-in module. The 6-axis condition really provided a way to create a plug-in that would be able to stretch multiple modules, and as it rotated across the facade, potential facade, it would be able to facilitate actions such as a brise-soleil or a water collector. But as we just started to look more and more at this, we started to realize that we really wanted to focus on developing the primary module itself and really look at this as something that could be a future development and study of the module itself.
Yeah, and so here's sort of what we deemed as like the critical diagram, I think, of the entire project. It's showcasing the intent of all of these ideas that we kind of worked through, working in tandem, trying to push the limits of, again, going back to that original kind of question of what are the limits of controlling and leveraging water flow on a vertical facade. And you can kind of see better diagrammed here that, you know, because it's, you know, it's a two-faced facade system, it's not only is it controlling, or at least kind of somewhat controlling the flow of water two-dimensionally up and down, but also three-dimensionally through these void spaces. And so it allows water to freely run through it. And on the left-hand side here, you can start seeing the full facade panel system as at scale. And the really, one of the cool things about terracotta is that it's a really fantastic material for evaporative cooling systems. And because we effectively increased the surface area of the panel by ridging them and allowed several opportunities for wind to be able to pass through the panel system, because again, there's a lot of void spaces here, this creates a really effective evaporating cooling system. And, you know, as a side note, the backs of the panels could potentially be unglazed so as to better provide, or to provide better thermal mass conditions.
You'll notice that this mock-up contains additional panels, which we developed later after we began to do a sort of meta-analysis of the original panel. As we began to finalize the ridging, we started to extrapolate what we would consider the language of the design. Once we determined what the base of this language was and what it wanted to be, we started to articulate additional expressions of the language. So to facilitate the funnel system that we had designed, we realized that we would need a support system if we wanted to make something that could be easily fabricated. So we asked, if the ridging's the sort of front of house design language, what's the sort of back of house design language? And we began to develop these structural tapered legs that would complement the funnel. The legs touch one another from panel to panel, and with an understanding that as they tapered, they would be both easier to release from the mold, but also continue the geometry that had been established with both the funnel and the edge-to-edge condition of the panels. The next challenge was for the structure to similarly embrace the hexagonal grid of the panel. Mario, if you could zoom in to drawing D, we can see that as we begin to integrate the connection detail into the legs, we use the length of the legs to stagger the connection points. This allows us to have a multi-layered structural system where the cross bracing is not running into one another. This then further allows for a wide array of variation in the connection system, including a predominantly vertical scheme, a predominantly horizontal scheme, and a hexagonal scheme in which any two given panels are connected only to one another. The leg design and connection detail itself also opens up to a wider array of more developed connection systems that could be used if it were to be used on a building facade. Once both design languages for front of house and back of house had been developed, it became very easy for us to kind of say, so what are the additional morphologies of this? And we were able to develop both a cornice component, a double leg component, and a single leg component. And if we go down to the axon below, you can start to see that in order to make sure that these panels all connected tightly without creating any kind of drip points between them, but also without creating too much friction between them, we began to explore custom silicone edging, silicone footing, and a silicone tongue that could begin to catch any water that would drip as it flows between two panels in the three-dimensional axis, which we can really see start to come to life as Mario brings us over to the 3D exploded axon. And so here you can see all of those components separated and the way that they would begin to connect together.
As we pull back in the space, you can see a series of studies that we created to explore the ways that the geometry of the module could generate a never-ending series of aesthetic options just with using two different glazing types. The final color combination and locations were narrowed down by our desires to blend the ridge geometries between a series of modules, and then its presence at our own office with a backdrop of the cream terracotta of the Wrigley building. So we can zoom in really quickly on that final model there. Thanks, Mario.
Mm-hmm.
In order to create this two-color option, we decided the concept of a resist. And that would be able to fit into the module once fired, giving for an ease of a glaze application and creating a separation that would keep the glazes from bleeding into one another. The negative of the resist then allows us to expose that base terracotta and contrast it with our glazes. If we then scroll down, you can see that we started beginning to do test glazes on the module's geometry. The glazes became integral with the ridging as we experimented with how the viscosity, the opacity, and the created nuances among the varied valleys and ridges were created on the ones that we had been studying. And then amongst the next series of photos, you can start to see the current process of creating the module, which is using the slip cast method. And just like the project before us, we had also took in the constraints of ram pressing, the process that could make it much more economical if we really wanted to produce these modules to a scale to really envelop an entire building facade. Next, we turn around and can see a building model that starts to look at a very lattice-like aesthetic quality that can start to be created as we jump up in scale of the application.
So our team decided to look at aggregating our facade module on the facade of the River Beach Tower, which is an ongoing research collaboration between Perkins and Will, the University of Cambridge, and Thornton Tomasetti. We thought it was appropriate to combine these two research endeavors for this exhibition. And our team looked at varying the density of our facade modules over the height of the building to showcase the adaptability of the module patterning and the ability to create areas of varying exposure and visibility.
So an aspect that has continually been important to our project was the ability to really create a scaleless product that would be able to continue to adapt and it evolved in both size and glazing type, as you can see with this gradient that we started playing with in some of these last renderings. We want to give a shout out and thank you to people at our office who are really helpful through this process. Nick Cameron, Jim Gabelhausen, Tom Ozina, Todd Snap, and then Joshua Stein, who has worked a lot with ACAW in the past, and his endless knowledge was really helpful to this process. Big shout out and thank you to Boston Valley, University of Buffalo, Matterworks, specifically John Krause, Sandy Brayman, Mitchell Bring, and Omar Khan. Thank you all for listening, and we can't wait to hear your questions.
Yeah, thank you.
Super.
Okay. Actually, so the PLP team is actually PLP with Christine Jetten from over in Holland, who's a renowned and very talented ceramicist. Is Christine on? Can you shout out, Christine?
Say hello, Christine.
Hi, I'm on, yes.
Okay, great, because you're going to do a bit of talking later on and relieve us.
Sure,
and
yes.
hopefully you can all understand my accent over here in very moody London. So PLP Architecture, we've actually worked with Christine quite a lot before, and we've always had a deep fascination with terracotta. We've actually done quite a bit of work in terracotta too, but usually it's applied very statically as a cladding to a facade. And working with Christine, we asked the question, how do we take best advantage of what could be a very special glaze? And that became our focus. And one way in which we could take advantage of it is light, in the way light registers when it hits the surface of the glaze, and reflectivity and that kind of thing. And we know that light is actually a very fluid thing. It's not static at all. And there are games to play by faceting surfaces to create a dance and play and shimmer with reflection. And when you do see buildings which do have glazed ceramic facades, you often see that those areas where daylight or sunlight is actually hitting the facade look very different, register very different to where the sun is not reaching. So that led to two initial ideas from us in the idea of creating a facade system, a standard facade system. But to create the kind of dynamism that we're interested, what do we do? Number one, we'd like to move the tiles so that we play with the reflectivity potentially to create that dynamism. Number two, we like the idea of producing a kind of sculptural composition of tiles so that it expresses that dynamism too.
So this idea about how the tile surface could be sort of developed and have some qualities that were sort of from more than natural aspects of the world, and being able to reflect light in non-standard ways, started us thinking about how to go about looking at the actual three-dimensional surface of the tile. So we looked at some inspiration from nature, whether it's grass or sand or water. And we then sort of developed some others that were slightly more esoteric in looking at the way that water flowed over a surface when sort of influenced by air patterns, actually. So there was quite a broad range of material that started to inform a series of studies on what we agreed quite early on would be a very regular geometric grid. We had a lot of conversations early doors about the number of things we were trying to attempt within our proposal, and actually we felt it was quite good to keep the regularity of the grid and the size of the module relatively straightforward. So that sort of set us up to start testing various manipulations of the surface of the tile with some of these patterns that we'd started to draw inspiration from. You can see these became quite wild, and we went through quite a lot of permutations until we got to this one where we kind of liked the undulations that were formed on the surface. There were areas of it that started to have an element of repeatability to it, but also it very strongly, even in this very early mock-up, showed a light and dark character. But one of those early conversations we had as well was that actually we've got 64 different tiles here. This is not a very repeatable pattern. We then decided to look at whether you could develop an array or grouping of tiles that could form a more organic sort of surface, or what appeared to be an organic surface, with either a rotation or a different sort of arrangement of the tiles. These were some early studies which I must say we found a little bit unsuccessful, but as we carried on with this, we ended up with this on the top left, which was a study that ended up with only 3 different tile types that, through an arrangement of either turning through 90 degrees or orientating on the grid, we found we could create a surface that looked quite willful or quite sort of natural in its response. That grid was quite easily translated to this, which became one of our first working drawings for the guys at Boston Valley to start looking at, and for Andy to start studying. So we ended up with 3 tiles in total that, once arranged in this pattern, gave us our sort of tile surface. There was quite a lot of development work that went on to inform how we would then arrange the tiles, how we would hang them, and Daniel will talk a little bit more about that in a minute, but this drawing shows how we sort of developed the single module. We did a small amount of testing ourselves. We don't profess to be terracotta manufacturers, but we did some 3D printed molds, which we used some air drying clay just to start to test the surface and to see what the subtleties that we got in the surface were. And you could see from this example that the faceting from the model was actually quite apparent in a very fine grained material like terracotta, or this particular clay we were using. It showed quite nicely some ridges and valleys, and whilst it's a bit rough and ready, it kind of gave us a sense that we were going in the right direction.
Yeah, back to the idea of moving the tiles, and we kind of like the idea, rather than just poking the tiles through human intervention or something like that, we like the idea of sticking with the kind of like dynamism from nature, but you kind of like start to see expressed in some of those compositions we showed. We like the idea of the facade being moved by their environment. That could be, for instance, here in the Institute of Monterab, where these apertures are controlled by sunlight hitting the facade to protect the exhibition spaces within. Or this is quite a nice building that we have here in London, or intriguing at least from the point of view that this is a veil of little metal panels, which is in front of fairly nondescript facades, but which, as the wind blows, you get this kind of like rippling and shimmering effect, which is very nice. So wind creating that movement there, and we like the idea of doing something different and doing something that moves by temperature. And so we started to think about ideas for how we might do that. There is gas struts which open the vents in greenhouses. There's thermobimetallic strips which could somehow help us move things if there's enough strength behind it. And then perhaps simply a thermostatic radiator thermostat, rather, which has a thermostatic valve within it, which might help us. And this is a very early mock-up we made of a tile, which we put a radiator valve behind it. And as we heated this up with a hairdryer, it actually starts to open up, which is quite fascinating, but not very controllable. So we actually went back to I don't know if you can see me on the screen, but we actually went back to the idea of a gas strut, which felt a little bit more manipulative, possible to manipulate. So we started playing with hot water and cold water to see what the opportunities were for using that as a little poking device for opening up our tiles. So where we started to arrive at is an installation. This is the mock-up installation, what you see on the right, virtual now, but we planned it to be like procurable easily, so that we can actually do it on the day. So the idea is a load of tiles which are pivoting on a rod, and those tiles, some of them, due to being poked in the back by these probes which extend due to temperature increases, start to open up some of the tiles, push them open, so that they register a very different, very subtly different reflection. And these different probes might have different kind of offsets from the back of the tile, so that they don't all open at once. They kind of like gradually open. So this is a bit of a close-up of what that might look like. Let's see if we can get this video to work. We're very low-tech here, but I think you can just see these very slowly, actually, sorry, where you can see the tiles starting to open from the back. Just now on. Thank you. So I don't want to bore you with the details of the installation. Suffice to say, we looked at ways in which we could do this cheaply and easily. Obviously, if this was to be applied to a real facade system, we would do it differently. But here, for the ACAL workshop, we were planning to do it in Unistrut, which is very easily available. So we developed it as a 8x8 checkerboard of Unistrut components and tiles being threaded through.
So a little bit on the glaze character. When we work with Christine in the past, we often sort of start our process with talking about what's inspiring us for that particular project, and these references can quite often be very abstract, and our process over the years has shown that almost the more abstract we get, but tries to focus on certain ideas, the better informed the process with Christine goes. So we were quite keen on a facade that, whilst the overall surface registered something that was quite organic and quite sort of weathered looking, the actual components themselves were very technical and very sort of technology driven. And you saw from Daniel's earlier slide, the back of the system was very important. So seeing the rear was quite nice, and it's very high-tech facade in that respect. But the surface quality for us had to be something that reflected that sort of strength of character, but also had an ability to reflect and change, but with very small degrees of movement. So these are some close-ups of the space shuttle and its belly after it's been through, entering the atmosphere again, and the tiles get burnt and scorched, and they take on much different characters from one another, even from one to the other. And the sort of array nature of this was quite nice as well. So in its basic form, it's a little porcelain tile, and then as they get sort of damaged, then they get screwed on. So you can see that it starts to talk about some of those elements of character we were looking for. This also shows the surface of the underside of a spy plane that has that sort of technical aspect, in that it's a series of elements, but also it takes on qualities of the material that it's made from. And also those materials and those shapes can actually express quite organic forms when they need to. We also quite like this image, is that it's a very sort of man-made element, but also it combines qualities that are also very sort of elemental. So the steam and the water and the fire that drive forward something that's very man-made, but that kind of dark gunmetal texture is quite intriguing. And then this final one of a small sample of quite an old piece of terracotta, fired with a glaze that is still quite nice today, but it seems weathered and has taken on a certain character. So at this point, I'm going to hand over to Christine, who will talk a little bit about the process that we were going on in Europe between herself and us, as well as the process we were developing across the pond as well.
Wayne or Dan, could you manage the PowerPoint? Thank you, thanks.
Yeah.
My experimentation started from the visual references we collected, and by trial and learning, as a kind of the way I followed the process. And this slide shows how I wanted to capture the design intent for this robust industrial look with the patina surface. And we were looking to both reflective and matte. So I went to several passes before I got this result. And what I like to add is how I enjoyed the process of engaging the architects in the designing of the glaze. At this time, we were still in the process of designing the geometry of the tiles, and therefore I started the glaze research on random test tiles that were available in my studio. Next slide, please. And as this shows, it's like all about nuances. So here I'm studying the metallic look to get more black and to understand how the minerals in the clay body can influence the glaze. So if you look at the left image, it's about the same glaze. At the left side, put on a tan body, and at the right side, put on a dark brown, black firing clay body. Yeah, next slide, please. So now in the meantime, we were discussing that the backside of the screen also needed a visual quality. Like one could see at the facade of Institut du Monde Arabe in Paris. So this is why I continued the testing on these two types of clay bodies, being a red firing and a black firing clay body. And I was interested in how the black firing clay body could influence the visuals of the glaze. And we also wanted to research the faceting. And that's why I chose these test tiles that allow the glaze to pool, to bring out the several characteristics of one glaze depending from the thickness in application. So where it pools. Okay, next please. So I continued testing the surface also, surface qualities that influence the light responsiveness. And I like to add that most of the time my research starts from scratch purposely by just mixing the glaze minerals, because each glaze recipe contains a collection of glaze minerals, in this case about 7, and they influence each other in the firing process. So in that way we can control it, but also get new visual qualities and sometimes surprises. And I like to also to get the surprises to further continue the design. So then later in the process, when I get the visuals right, then I start bringing in the chemical formulas and the ceramic technology, as Andy Brayman explained yesterday. In this case, I used the ceramic technology as a tool in the designing. Next slide, please. Here is another design intent, the bluish metallic reflection. And I studied this while I was refining the glaze formulas. And next one shows, next slide, how these tests show like the fluidity of the light, which we wanted to get work for us in the design, because we wanted to make the building really highly attractive as a visual experience. And skins of buildings do have this ability to influence people's daily routes, the social sphere, and they can be emotionally engaging, stimulating the senses, like a building becoming a place where you like to get back to. So that's what we wanted to bring into the design. Next. And now we were getting close to what we were looking for in the industrial black steel, such as was shown on the detail image of the locomotive. And at this stage, because we were getting more close to what we wanted to capture, I started using a Boston Valley's glaze material, of which I had a few kinds in stock from a former project, and a few of them are part of this recipe, to bring us more close to what we could achieve in the industrial production. The results of these tests were not quite right yet. They were lacking the blue metallic. And in the next slide, It shows where the blue metallic is included again, and the images show both in overcast and sunny weather the glaze response to light. And from this point, I left it to Andy Bremen. I handed over the process to him because now it was time to continue the testing in the industrial production with the actual material used by Boston Valley Terracotta. Yeah, that's it for this part.
Thank you, Christine. So the final
PLP,
few slides.
can we move towards wrapping it up?
Sure, no problem. So the final few slides just talk through some of the tests we received from Andy, and this first set came through, and the thing that intrigued us most was sample C, where from a head-on view it looks quite nice and dark and that kind of quality we're looking for, but actually in the oblique at the bottom you can see it had that very highly reflective quality. So that was a sort of direction we gave him, and he started to do some early tests of the molds also, which were the faceted geometries that you see here. We put this little one in down at the bottom because it looks like a little funny face. It's a test of what the back of the tile could be. And then the results. So we only got these pictures a couple of days ago, so I'll go through them pretty quickly. So there's an example of the tile itself. The valleys and the troughs in the valley have come through very well. There's the back of the tile, which is rather handsome. There's a nice cut through one that shows the geometry. Here we start to see them arrayed, and these two images really, I think, help because on this one you see that there's areas of dark, the tiles look very matte, but only a very fractional change in the camera orientation shows quite a big distinct change in the character, and the reflection of the light is some more zoomed in shots of the surface of the tiles, and you can see that ebbing and flowing of the glaze as it's melting and working its way through the various sort of undulations of the surface has created something rather lovely. Well done, Andy. Well done, Andy. So we've got one final bit to show you though. We come out of the presentation. This morning, they whisked their way across the pond, but we actually have one of our sample tiles, which you can see here is nicely reflecting the light. And we actually managed to put it on a rod this morning as well. So there's the back. And the idea would be that we have our lovely piston that would push in here. And once it does that, it starts to reflect and the character of the glaze really comes out. So in lieu of actually doing this in person over in your side of the water, we thought we'd try a small one this morning. Thank you.
Thank you very much. No, that was quite beautiful. So let me see if we can have everybody just turn their videos on, and I'll have the attendees be able to sort of see everybody. I think it's just if those that were on the panel turn their videos on as opposed to all the panelists. So maybe I can just get something started here. I know that there are some very practical questions that are being posed also in terms of costs and so forth. But I wanted to take on this question of kind of a interest in architecture on surfacing. In some cases here, there's the desire for the dynamism of a surface, physical kinetic movement, but others is visual movement. In the case of Perkins and Will, the movement of water or the movement of the environment in some ways around these surfaces. The increasing I would like you to sort of maybe reflect a little bit from the materials point of view, because clearly you can do a lot of these forms in perhaps cheaper materials. And I think some of you are beginning to sort of suggest why this material as opposed to GFRC or something else. Could you maybe reflect a little bit, because I'm sure you've worked in those other materials, how this material is beginning to sort of bring you value and issues to the construction of these surfaces?
Well, I think for Perkins and Will, one of the biggest things was, I mean, obviously the aesthetic value, right? Like you can't get the glazing effects on any other materials that you can get on terracotta. Also, the thermal mass that terracotta provides is something that is like miles ahead in terms of like the fabrication opportunities as well as the cost. And you know, again, because of that thermal mass, you know, it creates a really good evaporative cooling system, or allows for a really good evaporative cooling system in regards to how complex you can get with the geometry, much like our panel. Like our panel is, in regards to everything else, it's a fairly complex piece of geometry, and you know, it's able to be fabricated via slip casting or ram pressing, which, you know, it would take a lot of, we're actually doing an experimentation out of our panel in one of our material sciences lab, being fabricated out of GFRC, and we're actually running into a lot of problems. You know, so I think that's from Perkins and Will's perspective, what the value of terracotta brings.
Handel?
Yeah, so I mean, I think Mario touched on it in their initial presentation also. You know, one of the things that we've talked about early on was the fact that essentially with a rain screen system, one of the challenges is ventilating that wall cavity. And, you know, for us, one of the motivations, you know, for kind of looking down the line at this system in its kind of sustainable advantages is the fact that, you know, by having this system that opens up, you can use those thermal qualities of the actual terracotta material to, you know, mitigate some of those issues by dilating the wall in certain locations to like purge that heat that builds up within the wall cavity. And, you know, I think that, you know, the other thing that Mario said that is very true is, you know, that the glazing opportunities that you get from using this terracotta material are really what we were super interested in terms of like deploying a kind of color set on our pieces, on our single piece, that then when tilted at different angles would register as a different color or a different tone. And, you know, that is definitely a parallel in our work to PLP's work as well. You know, I think just in the kind of a different, you know, we were really worried more about just the kind of module as it moves rather than the kind of, you know, kind of interaction of the actual surface in the singular module as well. So, you know, like one of the images in our presentation, as you can see in our exhibition space, as these pieces change, it's all one glazing color, but as it pivots, you really start to see that kind of material registration shift from, you know, one tone to another, which I think is something that would be very hard to get that shape and some of the performative qualities and that glazing finish in any other material.
PLP, I think you have pushed the limits on, and it's wonderful to have Christine, who's a longtime supportive of ACAL, be a partner in this. But could you speak a little bit to your work in that regard?
Like I said before, we've worked with Christine quite a lot, and we do enjoy the process. And I think, you know, we could only echo the statements that others have made on the use of terracotta. I think for us, it's also quite nice that it's a natural material. There is a process to it. You know, it has to go through a number of forms to get to where it is. It can be equally warm and cold. It's versatile. It's recyclable. And certainly for us in the UK at the moment, it doesn't set on fire, which is a practical concern. That materials like GRC, for instance, are, you know, they bring challenges. I think with the glazes, you know, it opens up a sort of infinite world of what you can do with the surface. And invariably with most other materials, you are relatively limited in where you can end up, whether that's the surface form, the three-dimensionality of it, or in its look and how it performs. I'd say also it's an extremely durable material. I think someone said right at the beginning, you know, we're still finding clay drain pipes from thousands of years ago. I mean, for us, that idea that our buildings are still going to be there in thousands of years would be quite a nice idea, actually.
Are there any questions you have for each other? As I look through the chat has, I think you're also doing a good job of responding directly to it.
This is Ted. I just want to say, especially the answer of glazing being a big factor in it. PLP's glaze studies are phenomenal. That glaze looks amazing. And Handel, I think, Paul, you mentioned that the flipping effect, having the two sides of the glaze, like I think that adding that glaze isn't a 50% increase or a 200% increase on the facade. It's a 1,000% increase in how like sexy that facade looks. It's more than the sum of its parts.
Right.
Yeah.
Appreciate that.
I mean, yeah, I think all of the work thus far has been really fantastic, and I think that's been the really exciting moments of this as well. Outside of just us being able to design with this material, is seeing the depth and breadth of material research, design and capabilities of all of our offices kind of together, which hopefully the people attending will be able to see in the that EXC that we'll be providing.
Yeah, I guess I have a quick question for the Perkins and Will team. We both have kind of dealt with some tensile cable structures in terms of being the backup system. Was there any like lessons learned in your guys' process about like trying to deal with the connections? And we ended up kind of getting in a bit over our heads in terms of trying to do this with all off-the-shelf parts. And I think if we were to do this again and know that we wouldn't have to be building it ourselves at University of Buffalo, we would have probably taken a different approach to the actual node itself. So I'm just curious to hear what you guys went through relative to the actual tensile cables. Yeah,
so I think for us, actually most of the kind of design of our support structure or support system was those kind of struts. And so just like you were doing with the off-the-shelf components, we actually integrated that as part of our panel itself.
Yeah.
And because we're like, we have the capacity to essentially fabricate any geometry that we want, so long as you can remove it from the mold. So like, let's see what we can do with like integrating that structural component. Like,
right.
I mean, I'm not 100% sure if we're going to need any more kind of structural like rigidity to that strut. We have to test that with more and more pieces. I'm pretty sure we will, but I think that's for us to kind of really figure out.
Totally. Yeah. I mean, it's exciting. I think, the potential of, finding a home for these ideas is something that's really cool to contemplate. And hopefully everybody's able to, at least get some sort of mock-up together in the near future.
For sure.
That's our hope, that we do have some opportunity to really do the mock-ups. Well, I'd like to thank the three teams. The work is phenomenal and very exciting.